Hey, hi everyone. Very good evening. Hi Anil. Hi Jyoti. Hi Harsh. Hello Srisha. Good evening. All right. So, yes, my voice is loud and clear. As my voice is loud and clear to everybody. Great. Wonderful. So, let's get into today's topic. So, what are the things we have covered in yesterday's session? Can you all do a quick recap? Maybe the topics. Can you post it? What are the things that we have discussed yesterday? And if I give any task, if I given any task, what is that? Can you all post it? What are the topics we have covered in yesterday's session? So Anil says CNN RNN. Oh, did we discuss about RNN theory, Anil? Really? Have we discussed about RNN? Then why we have mentioned RNN? Harsh, Conva matrix features max scoring. Correct. Convolutional network CNN architecture. Okay, wonderful. So let me ask you some questions. So why convolutional neural network? Why CNN? Why CNN? Why CNN? Okay, Srisha says extract essential data from the input data. Right. Image classification and recognition. So yes, but the right answer is why CNN. The major point what we have to say, feature extraction. Great, Jyoti. To extract more features. Yes, Kyle, right. Rishikesh reduces the number of parameters without losing the quality. Oh, is it so, Rishikesh? It's completely wrong because I'm losing the quality. because I'm losing the quality, but I'm extracting important features. Your answer is completely wrong. Why? Because without losing the quality of the image, I can't extract the features. All right. So we are losing some features. That's why we are the complete architecture itself, CNN feature extraction and max pooling layer. We are reducing the network. Got my point, Rishikesh? So what I mentioned yesterday is for feature extraction, we are getting into CNN. Harsh, because processing image variant is inefficient. Correct, right? Weight updating is in kernel matrix. Correct. Right. And have you all executed the line what I've given yesterday? Have you all tried it? Only Rishikesh tried. What about others? No one tried? Okay, Harsh. All right. Okay. So Jyoti. All right, Jyoti. All right. So can understand everyone's. I think everyone are busy with your studies and everything. That's okay. So I think only Rishikesh tried. So Rishikesh, how long it took to run your script? The architecture that we have got yesterday. How long it is taking? How long it was running in your local machine? Nearly around 1.5 hours. So for, okay, 1.5 hours. All right. And have you checked the performance? Performance, did you get chance to check it? Okay. All right, fine, no issues. So let me share you this. I think yesterday we looked onto the script theory of CNN network. CNN and max pooling, we can just keep consecutively and we can just add a number of layers. Yesterday we constructed CNN and then max pooling. Again, one more conva 2D and max pooling and then two hidden layers. And the last layer is nothing but the output layer we created. So in case if you have practiced it, then it should have been more appreciated. But maybe later you can do that. But now let me explain this particular part. Let me share. I'm not executing this line again, but if you look onto this, all right. If you look onto this particular screen, see this part, everything we have already done. So importing the necessary libraries, TensorFlow version, and then image data generator. We are just giving out this particular data path, and we are just doing it. And then we are looking into this Conva 2D. And then here we are having Conva, max pooling, Conva, max pooling, Conva, max pooling. This way we can have it. So anyway, any network architecture you can build it. And this is my architecture. Now I'm just choosing Adam as my optimizer, categorical cross entropy, and metric is nothing but accuracy. Now when I'm just running this for classify.fit, so X is nothing but directly training folder. What is this training folder? That's what I just saved it. Training folder. This is the name where exactly along with the path I've given it. So I'm just giving training folder. Epoch extend validation data is nothing but my validation folder. Steps per epoch is nothing but for one iteration, how many times it need to go forward and backward. And validation steps is nothing but 5. And verbose equal to 1. So when verbose is nothing but the number of the number of informations, how much informations that you are just you wanted to see, that's what verbose is all about. If you're giving number 10 and 15, the display 28, 13 milliseconds, 13 seconds per step. And in this way, you'll be getting a lot of few other details also you'll be getting it up. I'm not executing it because it will again take a lot of time, maybe 5 to 10 minutes, it will just take it. But I've just already ran it for 10 iterations. After running it, this is the next step. So we have to, if it is a machine learning script, we have to take it in a pickle format so that it is going to get converted as a binary file. So if you're working with images and videos related data, we have to take it in .h5 format. Now what I'm doing, so this is the name what I've created, classifier. All right. This is the name what I've created. That's where the intelligence is available, complete architecture. So now what I'm doing, so classifier dot save. Save is nothing but again it's one function which is already available within this Keras. Now there's nothing but the name I wanted to give it. So with respect to this name, now it is a binary file. Now what I'm doing, the next part is nothing but making prediction. Now what I'm doing is nothing but I'm just loading my particular model from keras.models. There is something, one package which we have to load. There's nothing but load model and import NumPy library. I'm just importing it up. And then from keras.preprocessing, because in the backend also, whenever now the intelligence is having it. Now in the backend, we have to write the steps one by one, right? So what need to be done, how the result need to be shown. We have to write it in the backend. So this script is completely a backend script. Okay, now what I'm doing in the backend, step number 1 is nothing but first the user will need to load one image. Let's say with respect to HTML, you are clicking, you're making one button called load image. So now that load image is nothing but it need to take one path. So now what I'm doing, so this is the path, D image test folder, Superman, this is the image what I'm giving. And the target size also 64 by 64. Why? Because that's what the size here I've given for target size. So this is another script which today we worked on 128 by 120, I think so. This is another script which I'm showing you because 128 by 128 was taking a lot of time. So I made it with 64 by 64 just to understand. Now this image will get read from this particular path and it will be stored over here. Now images need to be converted into arrays first because it will never be, again, it's a backend script. User is going to upload one image from his site in any web application or mobile application. So first image need to be converted to an array. So image dot, see this particular image, what imported from Keras, everything is used for pre-processing. Image dot, here you're having something called as image to array. What do I want to convert to an array? This test image. Now I convert it and I'm just storing it a test image. Now again, expand dimensions. Expand dimensions is nothing but test image is nothing but again, image to array. This is going to expand the image size by using 64 by 64 comma 3. All it comma 3 it is going to do because it is internally it is going to say, hey, this is a colored image. Internally it will be doing it. Now, after I get my image, I just done this particular pre-processing steps. I'm loading my intelligence, that is multi-class model.h5 file. I'm loading this particular intelligence. I'm storing into something called as model. Now I'm saying model.predict, that particular test image. After pre-processing it, we get into it. And finally, the result is going to get stored into this result. Because after pre-processing, I have to say whether this image belongs to which particular person. So the result will take a 0 or 1 or 2. That's what it will be taking. Now, If result, if it is nothing but 0th row, 0th column, because it's a dictionary, right? So it is working in row and column format. So 0th row, first column, 0th row, second column, sorry, 0th row, 0. So this is how it will be basically. If it is a dictionary, 0th row, 0th column, first column, sorry, second, third, fourth. So if it is 0, 0, it is Ian. If it is 0, 1, it is John. If it is 0, 2, it is Mary. If it is 0, 3, it is Superman. If it is 0, 4, it is Suresh. So now, finally, this result is having which value? Whether it is 3 or whether it is 2, what value it is. So let's say if this number, if it is 2, then this particular Mary will get triggered. And this if else condition, I think we already learned about if else and elif, everything in the Python session. So this thing will get triggered, and finally I will be getting an output of what exactly output. So here this is a very poor model what I just built, because actually the image is nothing but Superman. It should return Superman, but it's returning John, which is not able to understand the image properly because of bad quality of image, or the very reduced dimension, 64 by 64. That's what I'm reducing it up. So again, we have to fine tune this particular model. Able to get my point what I'm saying? Jyoti, Harsh, yes. Can I get a quick response from others as well? Able to get it? Srisha, perfect. Now this script, take it and execute it line by line. So I can share you the script. It should be fine. You will be able to get it. Now again, what you can do to take the performance, again use a matplotlib, model.history, accuracy can do it, plot legend. History object is not subscriptable, but you can try it out. It will be coming in because later I just executed it. I'm just getting an error. But what you can do is nothing but, so here you stored in this model. So model dot, you will be having only okay, here validation loss and validation accuracy, I'm not getting it. Maybe you can just plot with respect to loss and accuracy. That's what you can do. Separately, you have to do accuracy and then a legend show this particular part. It will be, you would be able to see that particular thing. All right. Now, even you don't need to give this. So that's what the point. So I'm not executing this, but I'll share you this material with you all. You can see this kind of graph, how exactly with respect to epochs, the loss is fluctuating, and separately, you can just take a look at how exactly accuracy is fluctuating. Okay, and with that, we can come to one conclusion. So this is the prediction script, how we have to write the scripts in the backend step by step to make a prediction. All right. Perfect. Now from here onward, so we will just, today's topic is nothing but yesterday till now. Let me do a recap with respect to what we are studying in deep learning. In the deep learning, we understood the basics of biological neuron, artificial neural network, different optimizers, loss functions, activations we learned. And then we came into this, we built our first ANN network, that is MNAST data set we picked up. Digit classification we have done. There we got an understanding, and yesterday we got into the CNN theory. We understood why CNN and what is the drawback of standalone artificial neural network without CNN, what is the drawback, we learned it. And then we got to understand how exactly CNN architecture will look like, and we went into the mathematical discussion, what is getting applied, how max pooling layer is working, and everything we discussed. And yesterday we worked with respect to one network manually. So now what had happened is nothing but in 1998, so researchers, they came up with their own networks. All right, they came up with their own network, and they just participated in one competition, and they, with that network, won that particular match, or we can say the competition. So what is a network? It is a very old story, and from that time onwards, a lot of new networks came into the picture. The very first network, what they have defined, and when they said it is the best network for handling black and white images, it's nothing but we call it as a LeNet. Okay, let me share this material. 1 minute. Let me share this. Look onto it. In LeanNet 5, it's nothing but a 1998 developed by Lakeon. So the objective of LeanNet 5 is nothing but to recognize the handwritten machine printable characters to make a classification, whether it is A, B, or C, or D. It need to make a classification. What is about LeanNet is nothing but LeanNet 5. Why it is 5, we'll understand it in some time. Used to classify 2D images. 2D images nothing but what? Black and white images, because there was no GPU in 1998. Only they had black and white images. So to classify this black and white images, for that purpose, they devised this particular architecture, and it had won that one competition there. So the network has 5 layers with learnable parameters, and hence named as DNet 5. Okay, here TANH activation function is used. So the researchers, they used the TANH activation function for the network. Architecture have 3 convolutional layer, an average pooling layer, followed by flattening layer and 2 fully connected layer, and output layer consists of softmax layer. All right. So for training dataset, again, they have used what is the it's nothing but trained on modified MNST dataset of 70,000 handwritten digits itself. So now what we can do, let me share you on another screen how exactly the architecture look like. Look onto this. So this is the architecture of this LeanNet, where exactly they are having input images of size 32 by 32, and they are applying a conva of 6 features. And because of 6 features, and at that time there was no concept called as padding. Okay, there is no concept called as padding. So they are applying this conva, and six such conva filters they are using it, and then subsampling is nothing but they are using this average pooling layer. So from I have size 2 by 2 itself, and the size is equal to 2, so 28 by 28 will be reduced to 14, and again one conva layer they're using it. So but 16 such filters they are using it, and because of that, because of no padding, the image size getting reduced 10 by 10, and then again average sampling, so from 10 by 10 it will be reduced to 5 by 5. And again what they're doing, they're using this fully connected layer, the full connection they are just trying to do, and then 10 output layer. So that's what the connection is. Now let's take a look at this particular connection, and let's build our own network. So this is 32 by 32, and conv of size 5 by 5, and then this multiplication is going to happen. So what we can do, let's try to build this kind of network manually in one Jupyter notebook to understand this more better. So what we will do, let's all open up a new Jupyter notebook. Let's all open up a new Jupyter notebook. So this is the very first architecture which got released into the market at 1998. Let us construct the same thing to understand this, how we have to construct any network manually. Let me click on it. Deep learning. So here, let me give a name, new Python 3. So let me give a name like LeanNet 5 architecture. All right. So the very first step is nothing but import import necessary libraries. So today's session is going to be more scripting and less theory. So let's import this particular part, and also let's import the necessary libraries here. So what are the things I want is nothing but from TensorFlow. We want this Keras, import Keras. So this one Keras we wanted, and we are going to work with this MNAST dataset. So how to do this? Maybe from Keras dot, if you give tab button. Okay, first let me import it. It's getting imported. All right, now Keras dot. We scroll down datasets, you're having it. Import. This is another way. Import, if you give Boston House, CIFAR, CIFAR 10, CIFAR 100, you're having a lot of datasets. Let me import this MNAST dataset itself. And then what are the other things? We need the sequential. So from Keras, import that's sequential. And then layers from Keras dot layers. Let me import this convert 2D. Convert 2D. And now they are using something called as average pooling, right? AV, let me type it, says average pooling 2D. And then we will be using this flatten layer and also dense layer. So this part need to be, it will come automatically whenever you're just practicing it, okay? Now we import necessary libraries done. Now the next step is nothing but import dataset. How can import it? So here MNST you have imported it, right? So I'll just do this particular part, MNST dot, if you give tab button, load dataset. You're having load dataset, so let me load it. And this returns, see this 4 outputs, and we have already read it. It is going to return 4 outputs, tuple of 2 data. So the first one is nothing but you can take a read on it. Keras .io get started, Keras API reference, built-in datasets. See this MNIST and CIFAR 10. These are all the data set which had got applied over here. Let me click on it. So what even this also one way of doing it. So that way also we can do it. So this is a tuple of NumPy arrays. So X train and Y train, X test and Y test. So this is how we have to take it. That's what it is. So this X train. Sorry, this till this particular part it is X training data. And for that X train, I'm having Y train, that is output. And again, X test, that is a text data. So this particular part, it is text data. And for that, I'm having output. Okay, so let's take it in the same way. Tuple format, X train, comma Y train, comma X test, comma Y test. All right. Now I received this particular part. Now the next step is importing data, data understanding. In data understanding, you can just check that out. That is X-train dot shape, comma Y train dot shape. So it is 60,000 images of size 28 by 28, and this is what it is. So now what we can do. And also you can just check X test dot shape, comma Y test dot shape. Okay, 10,000 28 by 28 size and 10,000 by. So now, but if you're reading the theory of it, so actually this data set has been built on top of for digit classification. So not digit, alphabet classification, whether it is A, B, C, D, or E, or F, but that data set has been taken out. All right, that data set we are not having it here. So because if you see, that's what I've just shown you this. That data set has been outdated. So A, B, C, in this way we had a data set earlier, and that's what it has been trained with. If you're reading it, The major task what they have done to recognize the handwritten and mission printable characters. So mission printable characters, it can be numbers, it can be alphabets, what it can be anything. So what data we are having in our hand is nothing but MNIST data set we are having in our hand. So but the image size is nothing but what it is, 28 by 28. But what exactly the initially what they have done is nothing but they have taken an input image size of 32 by 30. That's how they have worked. So now what I'm doing, I'm just going to expand the dimension of this particular image from 28 by 28 to 32 by 32. How to do that? Because that's how the architecture is constructed. For that reason, I'm just doing this particular part over here so that the dimension it will get expanded. So how to do that? Again, to play with numbers, we are relying on, let me give fourth step, data preparation. Data preparation. So this one. So for playing with these numbers and expanding the dimensions and everything, we always need NumPy library. All right. So NumPy library, you can just explore it. I have not gotten much into this NumPy, but there is a NumPy library will be more useful in your deep learning part. So NumPy. All right. So now what I'm doing by using this NumPy, adding zeros, what we call adding zeros all around my matrix, we call it as what? Yesterday we learned it, right? Padding, right? So here also I'm having 28 by 28. I need to add padding is nothing but zeros all around. I'm not creating any duplicate values. Just I'm adding zeros. It is not anyway. It is not going to impact my data, right? Anyway, just I'm going to increase the size. That's it. So within NP NumPy, I'm just giving talk. I'm having something called as pad. Pad is a function. So let me take a read on it. Correct. So here pad and array. So array, what is that array we have to give it? And then pad width we have to give it. Array like, so let me give array is equal to, what is that array? Array and pad width, let me copy. So array is equal to my X string. That's my particular array. That's what I want to change it. So and pad width, how to do it? So it's a sequence of array like integer. So numbers of values padded to the edges of the arrays, that is before comma after and till before comma after. Unique pad width for each axis. So for each axis we have to do. So now what I'll do is nothing but let me take it in this way. That is yields some, see this before comma after, what exactly this will do, comma yields same before and after pad for each axis, or int is a shortcut for before and after is equal to pad width for all the axes. Okay, now we got an understanding. Now what I'll do, let me copy this. I just wanted to make it like the size, it should come like 32 by 32. That's what I'm just focusing on. So what I'll do, how exactly the answers are coming, it is returning me 10,000, sorry, 60,000 images. Do I need to pad the 60,000 images? The number, do I need to pad it? Just number, do we need to pad it? The 60,000, this number, do we have to pad it? No, we don't need to pad it. So what I'm doing, so the same format, right? So this one, I don't need to pad it. So let me give 0, 0 and comma till n we have. So let me just delete it. And this 0, 0 is for this 60,000. I don't need to do. But this one, 28 by 28, before and after is nothing but I'm just to the left hand side 2 and to the right hand side 2. Now it becomes what? Left hand side I'm adding 2 zeros and the right hand side I'm adding 2 zeros. Now it becomes 32 by 32. Able to understand? This part I have to touch it and this part also I have to touch it. So let me give a comma 2 by 2. Okay. Now let me again store this particular part. See? Okay. This one bracket. Now it got stored. Now let me store it into something like again X-train. Okay. Now if you look onto X-train dot shape, see this 32 by 32. Able to understand this point? How I've done and everything. Jyoti, yes. Perfect. Now this part I have to do it for again test data as well. Wonderful. Test data as well. So what I'm doing, let me copy this. Copy, simply paste it. Now here, this is my X test data. So the same thing here, I have to do nothing, 2 by 2 here, so that it will be 32 by 32. Right. Now you can check it out. Xtrain dot shape, comma, white train, the same thing. Check it now. Why we are doing it? Just to make sure it's 32 by 32, so that it is going to be okay. See this, why now it has become 36, because I executed this 2 times, because already it was 32 by 32. Again, see this line number 11. If I'm executing it again it will be increased. Line cell number 12, again I'm running it 40. See this is getting increased. So make sure it should be 32 by 32. So to update it, again what you need to do, again reload the data set. Check out the shape now, 28 by 28. Execute this line once, and now if you see 32 by 32. All right, now my input image size is ready. Now let's go, and one more part also we have to do. What is that? What is that we have to do it here? Data preparation. Yesterday when we worked on, without using the standard deviation, the result was something going zigzag, right? So let's also try to do the standardization process. Okay. So what I'll do is nothing but you can check it out. Xtrain dot std standard deviation, comma xtest dot standard deviation. Okay, 70.18. It's pretty high. I have to make it reduced. So what I'm doing, my Xtrain data, whatever I'm just getting it over here, I just wanted to divide it by 255. All right. Now let me store it to Xtrain itself. Xtrain. Similar way, xtest equal to 255. Now it is done. Now let me take a look at this Xtrain in a 0th index. Okay, this is how it is. Fine, because inside the values it will be float numbers. Maybe let me try to take a look at the deviations. Xtrain dot deviation, come on, xtest, come on, standard deviation. Now it will be 0.27 and 0.27. Now the variance also got reduced. All right. Now what we can do is nothing but we can check out this Xtrain dot. This value is present inside. What is the data type of it? It should be float basically. Okay, float numbers. Fine. So now what I wanted is nothing but, so the data preparation step is done. Now let's go for model building, and we can just go in and build the architecture. So up to this clear, everyone, why I just done this particular padding and why I just done this normalization? Up to this clear? Perfect. Yes. Fine. So now day after data preparation, what is the next step? Fifth step is model building. So model building is a 2-step approach. First, build your architecture. Step number 1, build. Build your architecture. So how to build it? Sequential. You have to store it into model, and then model.add. What layer we have to add it according to the network? Convo 2D. Within this, if it is a first network, we have to take this particular input underscore shape, Control C, copy, paste it. But what is the network shape here? 28 by 28, sorry, 32 by 32, comma 1. This one we have to give it explicitly, which means that it is a black and white images. So explicitly we need to give it. And then what are the other things that we have to give it? Filters. How many such filters according to the network we have to construct at the first layer? How many such filters? It is 6 such filters. Let me zoom a bit. It is 6 such filters I have to create it. So what I'll do, let me create filters equal to 6. Next, kernel size. What should be the kernel size? Is equal to, again, let me go back. The constructed kernel size 5 by 5. That's what the kernel size. Let me again come back. 5 by 5. And then strides. How many movements they are doing? Only one. And padding. Padding, at the time there was no concept called as padding. So padding, let me give it like valid, which means no padding. And then activation. Which activation they have used? They have used tanh activation function. Tanh. Rest all things, let it be the same. All right. Now I added this particular input layer. Sorry, dot. Conv added it. Then it is average pooling. We already imported average pooling 2D. Now here what need to be done? Here pool size, copy. Pool size should be equal to, what is the pool size there? I think 2 by 2, right? Pool size, oh, here it is not given. Maybe let's take a look at this one. This will give us a perfect thing. Layer details, average pooling layer. So kernel size is 2 by 2, strides is equal to 2. Here they are going with 2 side. So let me check it out. Pool size nothing but 2 by 2, and also strides is equal to 2. Right. Now let me check out model summary. Let me take a look at it. How exactly it is looking like. So after this, the output of, see this, the output of convert 2D, it's 28 by 28. And the output of average pooling is 14 by 14 by 6. Is it right? Is it right? Output of convoy is 28 by 28. And output of average pooling is 14 by 14. You can take a look at here also. So 28 by 28. And after this particular subsampling, that is average pooling, it is 14 by 14 by 6. All right, great. So now what is the next step after this particular part? Conva subsampling, and then again a conva size 5 by 5. Now it is 16 such layers I have to create it. So let me create it. Now we are just practicing how to construct the network. All right. So now let me again copy this. Control C. Let me paste it. Now input shape, I should not give it over here. Let me remove that. How many such filters I have to create it? Second layer, it has 10 such filters. What is the kernel size? Again, I think 5 by 5. Kernel size is 5 by 5. Okay, 6 again. Is it 6 or 16? How come here it will be 16? I think it's a mistake. 16 such filters, I think so. Yeah, 16 such filters we have to give it. So filters should be 16. And strides 1, padding valid. Okay, this should be same. And strides equal to. Now if you look onto it, so 10 by 10 by 10. That's what the output of conva, because there is no padding concept there. And output of average pooling should be 5 by 5 by 16. Is that right? 5 by 5, 16 layers. Now the next point is nothing but I have to add one convolutional layer of 120 such layers I have to create it. So that's what the point over here. Let me try to add it here. One conva 2D layer I have to add it. So what I'll do. So how many filters? How many filters it is using? Feature map. Oh, feature map itself 120, and size is nothing but 1 by 1. Okay, that is 1 by 1 kernel size, but the conva filters is 120. So let me try to do that. Where is that? So here, let me copy. So 3 such conva layers. Execute. So here, how many such filters? 120 filters of kernel sizes 1 by 1. Strides is 1 and this one. Okay. Now see this. Now I got it. So 5 by 5 of 120 such filters. I got it over here. That's as per the network. Then what? 5 by 5 of 120. Then what? Fully connected layer. How many fully connected layer? and then okay, 5 by 5, then 5 by 5 convo, and then fully connected layer, we have to do it. So how many neurons they are creating it? 84 neurons they are creating it, and then 10 output. So that's what flatten it. So we have to flatten it. So let me then flatten this model dot add this flatten layer. All right. Now if you see 3000 neurons, I'm creating it after flattening model dot add. So how many neurons I have to create it at the first layer? 84 such neurons I have to create it. So let me create 84 such neurons. I'll be going this. Yes, 84 neurons, and then 10. 10 output layers. That's it. So create 84 such neurons. That is that is dense layer. Unix. Control C is equal to 84, comma this activation is equal to, again they have used tanh activation function, and finally model dot add dense layer units is equal to 10. Now what activation function? Here what activation function I have to use it? What activation function I have to use it? Is it tanh again, Srisha? Is it again Sigma Jyoti? How to choose between Rishikesh perfect, Harsh, Amal perfect? How do we have to choose between different activation functions? Again, I think so we missed it. So for multi-class classification, I think I'm repeating this for maybe 5th or 7th time, I think so. For multi-class classification, the output activation function should be softmax. All right, great. So now let me use the softmax activation function here. Right. Now let me execute it. Now my architecture is ready. All right. Now my architecture is completely ready. Fine. So see this one small change. The point here is nothing but according to the network, here we need to have 120 filters, but of size 5 by 5. Look onto it. Here, where exactly? Just observe this. 32 by 32. This network instead of this network, you can take a look on it. This size, this is perfect here. There is small changes here and there happen. 32 by 32. We're multiplying with 5 by 5 conva of 6 filters. All right. Let's check once with the network. So here, 5 by 5 kernel size, 6 such filters. Input image size is 32 by 32, and the output is nothing but 28 by 28. But 6 such filters you'll be having it, and then you're going to give it to subsampling. That is nothing but your average pooling layer. What should be the size of this? 2 by 2 and everything. So once it got to 14 by 14 by 16. Sorry, 14 by 14 by 6. So we got 14 by 14 by 6. And again, one more conva layer. So after this particular 5 by 5, now the output of this conva is nothing but 16 such filters I need to have it. After subsampling 5 by 5 by 16, right? 5 by 5 by 16. So 5 by 5 by 16. Now after this conva filter size, kernel size, it should be 5 by 5. There is a mistake over there. It should be 5 by 5. See this? 5 by 5. But how many layers I have to create it? 120 filters I have to create it. Right? So that's what according to. So here again here, it's not 1 by 1, it's 5 by 5. Okay, here it is. Sorry. Here it is. I missed it. 5 by 5. This is what I had to, I just looked onto this one. This one is perfect. 5 by 5. If you're doing it, what would be the output? Size it would be 1 by 1 multiplied by 120. So that's what the output here. 1 by 1, 120. and then I'm flattening it. 120 neurons I'll be getting it. That will be connected to 84 neurons and 10 output. This is a perfect network of linear architecture. Got it, everyone? Perfect. So now model architecture has been constructed. The next step is model compilation. Let's go and compile the model. This is step number 2. Let's give 5.1. And now it is 5.2. It is model compilation. All right. Let me compile this particular model. So model dot compile. So what are the things need to be done? Optimize the losses and metrics. Let me copy, paste it. So what loss function we have to choose? Let me choose the sparse categorical loss because my output it is in integers. So losses. Copy, paste it. What metrics? There are a lot of metrics that you can pick it up. So metrics, accuracy metric, binary, categorical, a lot of things is available. That will pick up accuracy metric. Now let it be RMS blob itself. Let me compile it. Compilation is done. Suppose compilation. The next step is 6-step model training. All right. Now in model training, what do I do? Model dot fit XY in batches. Let me copy. And validation data, we have it. Let me copy. And then that's what we find. Yeah, that's fine. So model.train, let me store epochs. Where is this? Very important. Epochs, we must see this. The default is 1. Let me give it to maybe 15 epochs. Let me go for, and my X is nothing but my X train data, and Y is nothing but my Y train. I think we got to understand batch is nothing but it'll take 50 images at a time. No, not 50 images. 60,000 divided by 50. So whatever the number is, the batches, let it be like this. Validation data, yes, I have. So I have to give it in a tuple format. So xtest, come on, how it is. Let me store this into something called as model training. And also this verbose, I think I've explained it, but I'm not when detailed it as auto. Let me give some higher number like 10 or something, so that we can get some extra result 10. Now let me execute it. Any problem? Okay, I'm not seeing the answers. Right, Kaushik. Epochs, it's running, but what about the result? Let me interrupt it. So let me remove this verbose out. Okay. Let it run. I'm expecting a loss, very minimum loss. And here, if you see 1200, Let's try to compare it. Here we have chosen RMS prop, right? So let's try to change to Adam also. So to perform this one iteration itself, it had taken 24 seconds time. Model training, it had taken 24 seconds time. Let's compare this analysis. 24 seconds for first iteration plus. So how we are getting this 1200? You can take it 60,000 divided by 50. You'll be having 1200. 1200 mini batches. It is just trying to take 24 plus 25 plus. Let's run for 5 epochs. That should be fine. Loss is 52, 40, 35. Okay, it's getting reduced. Let's see. This one is getting reduced. How about validation loss? Okay, validation loss also is getting reduced. See this? Earlier it was very higher, 87, 80, 78. All right. It's actually doing a pretty good job. So 24, 25, 24, 25. 24 plus 25. Let this get let it get run. But what I'll do, the same script, let me run it in Google Colab by changing it to GPU. Okay, and we'll see. We'll just calculate the timeline. How exactly this one is doing. Colab. Okay, Colab Google. Let me open this. I just wanted to check the performance time and everything. New notebook. I'm going to change the configuration to GPU and let's try to compare the performance time for model training. Okay, let me change this one time to GPU. Click on save and connect. Now let me copy this, all the scripts. Copy, paste it. Okay, execute this. And then this one, copy, execute this. Then shape and everything, it's not required. This one, I want to change it just to, here the goal is nothing but just to check the timing. That's what the point. And this one, let me do only the important operations. I'm just taking it and I'm just doing it. That's it. Okay. So this one is important line and then model architecture, copy, paste it, architecture and then compilation, paste it. Okay. And then model training. We have arrived at 9. Let me see. See this? 17 seconds. I don't think so. It had taken 17 seconds. 7 seconds. So GPU, that's why in order to deal with these images and videos, we need a good GPU machine. All right. Anyway, let's wait and see. See this one is at epoch 11. See for one iteration itself, it is taking this much time in CPU, but in GPU, I think this will get completed before that. All those 15 iterations. So this is something which Google is giving us. This is the power of GPU to deal. In case if you're getting selected in any AI-based companies, they will be giving you all this GPU-related configurations, GPU missions. They themselves they will be giving it to you. Okay. But for the purpose of learning, again, why Google Colab? As I said before, for learning purpose, we will try to use it. Okay. So we are at 10th iteration here. Gone to till it is going for 12th. Here we have arrived at 11th iteration. 13. See the loss also. I got down at this point itself. Okay, this is something fine, right? Now it got completed within 1 minute or 1.5 minutes. Still, I'm at 15th epoch, but here it got done. So this is the power of GPU. All right. So now we're able to understand why we need to get into GPU if we deal with image and video related data. This is one practical experimentation. Able to get it. Perfect. Now what we can do, we just wait for this. Okay, now it is done. So now let's check for how exactly this performance, how it is a performance and everything. Kaushik, can you explain the activation softmax, which activation I can use, which case? I think we've already explained this part, Kaushik. You didn't focus on the session, I think so. Just please focus on the session. I think I've explained already many times. So binary classification, go with sigmoid if you use only one neuron at the output stage. If you're using more than one neuron, we always need to use softmax activation function because of the mathematical equation which it holds. To know more about it, go back to my activation function session, learn it. It should be clear. All right. You have to go back to the activation session to know more about this particular steps. All right. Fine. So now this part it is done. Now I just wanted to understand how exactly the training had happened. Maybe, but before that, if you wanted to go for a prediction and check it out, how exactly this is doing, that also can be done. That also you can just check it out. That's not a problem. Let's evaluate it maybe. If you want, you can just go for the model evaluation. The next step is model training. Then we can say 7th one model testing or model evaluation. Model evaluation, let's say. So here model dot, there is one method called as evaluate. We can just give X and Y is available. So you can directly give copy, but paste it. X is nothing but my X test. Y is nothing but my Y test. Only this evaluation data. So this for my evaluation data, the loss is, okay, the loss is 0.8. That's what the loss. But again, it's 80% loss. It did not learn well, I can say. And this particular accuracy is 77% accuracy. Now that what's the point is, maybe what you can do, you can just try to go for prediction and just try to check it. Step number, next step is this model prediction script is pretty easier, all right, compared to prediction because it's already numbers and everything. Just use model dot predict. Model dot predict. Here, what data already are having this images. X test data you can give it. Let me take it in Y prediction. All the output it got predicted. Now what need to be done? Maybe let's specify any one number. So what I'll do is nothing but I just wanted to go with Y predicted of 29th index. Okay, so what is the 29th number? I would, if I wanted to see it. So what I can do, again, I need numpy. It's 29th index, np dot. There is something called as argmax, argument max. Argument max, nothing but which index is the maximum number, it is going to give it to me. It's nothing but 8. So this number, that is index number 29, we can check it out. X test of 29. Maybe you can just give it, right? Y test, that's where the answer is all about. See this, it is actually 1. It is a misclassification. Maybe you can just try with 100th index. Sorry, here 100th index. 100th index is fine, but here 29th index, it is not recognizing it. Okay, it is not misclassification. Accuracy is not pretty good. So that's what even we got to understand from the particular point. So again, let's look onto this model performance, 9 step. Model performance, what is this particular model performance? I just wanted to see. This part we already worked on it. So I just wanted to pull out matplotlib I wanted. So from matplotlib, let me import pyplot as plt. Let me use plt.plot. I just wanted to take this, since we are having validation and everything, in x-axis, this model training dot with respect to that history object, we can pull out accuracy and everything. The first step is nothing. Let's take with respect to loss, and val underscore loss. So that's what I want to plot in one graph. Let me take it. This one, and also plt.plot model.training.history. Nothing but validation, sorry. Val underscore loss. That's what the term. I got this particular graph, but I just wanted to give some titles. plt.show, but before that, what is my x label? plt.x label. There's nothing but my epochs. There is nothing but my iteration. plt.y label. There's nothing but my accuracy. Sorry, loss. It need to be reduced. And let me give a title. plt.title. Epochs versus losses, and I want to increase the size of this particular plot. plt.figure. Figure size is equal to the width wise. Let me keep it like 15, and height wise, let me keep it like 6. So now I got it. Legend, yes. Let me give a legend also. Come on, legend. Sorry, here I have to give something like label. This is nothing but my training loss. There's nothing but my comma label. Test loss, or we can say validation loss. So here, before show, let me use plt.legend as well, which I'm already having it here, legend. All right. Training loss, it's very smooth, but if you look onto this particular test loss, it's taking a zigzag path, which is not pretty good. And again, let me copy, let me check with respect to accuracy and validation accuracy. Training accuracy. Test accuracy. Accuracy. It. Now, if you see the way how it is learning, all right, the way how it is learning, it is very smooth. But even for the test data itself, it is taking many zigzag path, and it is not pretty good. But the look onto this particular path, the way how it is learning, it is very smooth. Is it right? Able to get my point? What I'm saying? Perfect. And maybe what we can do, there are a lot of reasons. Let me just make the script end, and let's get into the next one. But the point is that it might be because of a lot of reasons. Maybe you might have picked up a wrong metric, or wrong loss function you might have picked up. Or maybe you can try changing this RMS prop. Maybe try changing these metrics. Maybe let me try changing these metrics. So here, Since we chosen the sparse categorical entropy, so is there anything like sparse categorical entropy metric? Okay, here I'm having it as a metric. If we copy this, if we come back, oops, again, if I'm pasting it, it will take a lot of time again. Maybe in the meantime, once the model is getting learned, we can go for a quick break and come back. Let me execute this, or else let us keep two different files. Let me copy from this one, shift down arrow, let me copy it, C, and then before this end, let me make a division. And this even for learning and also test data also it need to learn well. So that's what I'm just trying it here. Let me paste it. Now what I'll do, let me change this model optimization. There are a lot of things. Maybe you can try changing to Adam here. Let me change it to Adam. Maybe let it be RMS block. Let me not change it. And here, let me keep it to the sparse categorical. Only this loss. Let me change. In this way, we have to try changing it, and we have to keep looking for it. And now model.fit. This will take again some time. It will take it. So now what we can do in the meanwhile, we can go for maybe 5 minutes break. We can come back. We can continue. Okay. Now the time is 8:17. Let's go for 5 minutes break and come back, and we can just look onto it how exactly this would work. And one more another architecture, the same way we call this an AlexNet architecture. We will just take a look at it how exactly that architecture is, and then we can wind up our today's session. All right. Fine. Perfect. Now let me start. 5 minutes timer. Yes. Let's go for break now. So I'm just opening a. Let me start it. It got started, so I can see this. And I'm just displaying this particular screen to just take a look at it. Let's go for 5 minutes break. Hey, hi everyone. It's all back from break. All right. So now let's, I think that this got executed. So let's try it now. Earlier, it was like 81 loss and 77 accuracy. Now, oops, loss is pretty much higher. 1.0675. Okay, for this one, let me make a prediction. Now it is making a prediction like 3. When the original answer is 1. Let me look at the performance. Again, training, the path is more smoother, but with respect to test data, not good. Let me take a look at it. What is it? Accuracy. History accuracy. All right, it is sparse categorical loss versus validation loss. And now it is sparse categorical accuracy versus validation sparse categorical accuracy. And validation sparse categorical accuracy. Okay, look onto it. For the training data, it was very smooth. Again, for the test data, it is something it is not behaving better. So this is but again, there are a lot of other ways also to optimize this particular network. But again, just try to read about something called as dropout. Okay, explore. Let me give some clue. Today's task is nothing but explore dropout function. All right. Dropout in neural network. Just try to explore it. This is one of the technique to overcome this kind of even validation score. Also, it will be pretty good. So try to once explore it and come back tomorrow. You can speak about it. Okay, this is the task for today. Got it, everyone, up to this? In this way, you can try with Adam Optimizer. Just check whether how exactly Adam Optimizer is working, what's the time it is going to take and everything. Just check it out once. All right, maybe let me check with Adam. Adam, it will do a pretty good job. In this way, you have to keep trying out. All right, to try changing your RMS prob optimizer, Adam Optimizer. In that way, try changing it and see how exactly the accuracy of the model and everything. It should be more better. All right. Great. So now, one quick task for everyone. Just nothing but let me show you another architecture. Now you have to try building it. Okay. After this, after this Selenium architecture, it comes the next architecture where we name it as. Let me show this. For dealing with this colored images, because till 1998 it is a black and white images. So here in 2012, so the researchers came up with an architecture called as AlexNet. Okay, so why AlexNet? Because the one who developed name is Alex. The person name is Alex. So this particular AlexNet came into the picture, and here the training data history we are able to have. The model was trained with 1.2 million images, ImageNet data set. It has around 60 million parameters and 6,50,000 neurons. The input of the model is nothing but RGB images. That is nothing but the colored image. The data is trained with 2 GPUs, 3 GB RAM, more memory, hence more it allows large network, even it takes 1 week for training. To reduce overfitting, fully connected layers is employed with the dropout functions. For again, I'm not going to explain dropout. Explore it and come back tomorrow. That should be great. For training, researchers use stochastic gradient descent as the optimizer. Here, real is the activation function used, and it helps improve the computation time 6 times faster. Padding was introduced from this AlexNet architecture. Okay, so the concept of padding was not available in the AlexNet for a LeanNet. Now we got introduced. Now let me show you the architecture of this AlexNet, and let's try constructing this particular part. So this is the complete architecture. All right, where exactly the input image size is 227 by 227 by 3. We are going with the kernel size is 11 by 11 and strides of 4. All right, and padding is equal to yes. See this? Every time we are just going to do the same padding. See this? Padding is nothing but padding. Every time we are going to do padding in this particular network. So, but let's keep this as a base. Based on this, let's try to do it. Okay. Let's create a new node, just architecture building. That is the task for now. Okay. Let me get into this. Let this be done. So, but let me open up a new notebook. Only architecture building, nothing more than that. Okay, I'm not going to take any data for color dimension, everything, but you can try that out with respect to the CNN architecture. What you've done, AlexNet architecture. So, what are the necessary libraries to be imported? First step, import necessary libraries. All right, let me import. Sorry, from Keras. Sorry, from TensorFlow. Let me import Keras. Yes, correct, Anil. Let me copy this. Thanks for it. So import sequential is capital. So, but here it is not average pooling. They're using max pooling layer from this particular network. Pooling layer is nothing but max pooling layer. All right, not average pooling. So let me remove this out to MA max. So to get the shortcuts and everything, first Keras need to be imported. Let me import it. Okay. I think since this one is getting executed. Okay, no. So now I got it. So from Keras, so this one also, let me hide this. So let me import convo and max pooling, because again it will take a lot of time. For that reason, I'm temporarily hiding it up. Max pooling 2D, flatten and dense. Okay. Now let me remove this. All right. Now this is all the libraries that that I needed. So two, it's nothing but import. Sorry, build architecture. With that, we are going to wind up our today's session. All right, architecture. We are going to build up two-step approach. It's nothing but we need to build a sequential model, and then which layer we have to add it, model.add this convo 2D layer. Convo 2D layer. It's an input image. That's what we have to take it. Input shape. Now, if anyone is asking you to construct your own network or architecture, this is how manually we need to do. What is input image size? It is 227. It's 227. 227 by 227 by 3, right? So let me go back there. So it's 227 by 227 by 3. Sorry, 3 colored image. And then what it is, filters. How many such filters? I think 11 such filters, right? Is equal to 11 such filters, and strides is equal to 4. Okay, let's try to do it. And activation function is reload. That's what we have already learned. Filters equal to 11, and kernel size is nothing but what's the kernel size? I think 5 by 5, 11 by 11. Okay, 11 by 11, and kernel size is 96. Sorry, see this? The filter size is 96. Filter size, convo filter size is 96. The depth is 96. 11 by 11 is nothing but the kernel size, convo feature size. Size is equal to 4. So let me go. 96 is nothing but my filter size. Kernel size is 11 by 11. And activation, maybe strides is equal to 4. 4 movements it is just trying to do. And padding is equal to yes. Am I giving padding? Padding, I think no padding. See this here, I'm not having padding. After pooling, I'm just giving padding here. So same is nothing but until this particular first stage, no padding. Here also no padding. From here, they are just giving padding. Okay. So let me do that. Padding is equal to valid, and activation is nothing but reload. That's what the theory we have learned. Right. So now the first one, model.summary. Let me close this. So 55 by 55 by 66. That should be the output of Conva matrix. Is it right? 55 by 55 by 96. Right. Now the next one is max pool of size 3 by 3. Strides is equal to 2. Max pooling layer of size 3 by 3. Strides is equal to 2. Let me construct it. Max pooling layer. Model.add. Max pooling layer. That the pool size. Copy, paste it, is equal to the sizes. I think what's the size? 3 by 3, 3,3, and the strides is equal to, I think 4, right? Strides is 2 here. All right, strides is 2. Now let me check it out. It is 27 by 27 by 96. Is it right? 27 by 27 by 96. Right. Now the next thing is I'm going to apply Conva. Here see the same is nothing but padding is equal to yes. And here the Conva feature, kernel size is 5 by 5, strides equal to 1, filter size is 256. 256, 5 by 5, 1. And padding is yes. Copy. To paste. Now I don't need this input sheet. It's 256 filters. And the kernel is nothing but, what is that? 5 by 5. Strides is 1. Padding is same. Reload. Done. Let me check it out. It is 27 by 27 by 256. That should be the output of Conva. 27 by 27 by 256 output of Conva. And then a max pooling layer of size 3 by 3, strides equal to 2. 3 by 3, strides equal to 2. So the same thing, right? I think this one is not getting changed. 3 by 3, strides equal to 2. So the output of this is 13 by 13 by 256. Is that right? 13 by 13 by 256. Now again, Conva of 384 filters of size 3 by 3, strides equal to 1. 384 filters. Copy, maybe 2 lines. 384. Kernel sizes 3 by 3. That's what according to the network, 3 by 3. And strides equal to 1, padding same, and reload activation function. That's it. And what about the pooling layer? Okay, see this after Conva, I'm not having pooling layer. Conva, 3 consecutive Convas. And 3 consecutive Convas is taking the same thing. 3 by 3, strides 1. 3 by 3, strides 1. All right. So that's what the point. And then after 3, max pooling layer, I'm having it. So let me give that consecutively. 3 by 3. 3 by 3. 3 consecutive, but what about the filter size? Is it getting changed? 384, 384, but the last one is 256. So let me change it to the last one. This one is 256. So rest all things is similar. And then max pooling layer. Max pooling layer of size 3 by 3, strides is equal to 2. The same thing. Now let me check it out. 6 by 6 by 256. That should be the output of max pooling layer. 6 by 6 by 256, and then flatten it. Let me flatten it. Model.add is flatten layer. Now after flattening it, 9216, is it right? 9216, and then a fully connected layer of 4096 neurons with reloads and activation functions. So model.add dense layer, the units is equal to 4096, My activation function is equal to reloop. So two such hidden layers I have. Let me copy, let me give it, and then model.add the last dense layer and the units. It's basically how many classification problem? It's 1000 basically. Basically, this network has been created for 1000 class classification problem. All right. Not we have constructed 5 class. Imagine how much time it has taken. So for this kind of network to process it and everything, we need a heavy GPU. So they have taken, according to the theory and study, they have taken 1 week to train the network itself. 1 week time. Well, even with GPUs. So this network, it will never run your local machine. 4096 neurons CPU power, it's not at all sufficient, but this is just an exercise to construct our own network. Okay, so it's a 1000 class classification. Let me come back here. So here it should be 1000. And what should be the activation function for multi-class classification? What should be the activation function for multi-class? Softmax. Okay, now take a look at the network. All right. Now we can just use compile and everything you can do. But the point is nothing but, given an architecture, would you be able to build it with respect to scripting? So this is how we can create it. All right, I just went step by step. I think if I'm explaining it line by line, it should have been, you might have not understood, but I have written it explicitly on call so that you all can understand it in a better way. But this is how we can create our network manually. Clear everyone up to this? Jyoti, understood? Yes. Yes. All right, perfect. So from here, let me give you one small term. Try reading about. So this is all about our CNN architectures and everything. I'm not going to get into that any other details, but there are a lot of other stuff which you have to know. In the first session, I've just given the terms. See, this is all the terms that that you have to learn. I've included some other topics. So there is something called as transfer learning. Okay, so transfer learning, deep convolutional model is nothing but AlexNet and linear. These are the very base model. So this model, I've just touched it. So from here, AlexNet and everything, just try to read about AlexNet CIFAR data set. But CIFAR is nothing but how to apply this AlexNet for this particular data. That is this website and built-in data set. CIFAR 10. All right. So how to apply this? You can take a read on it. And also, you can just look onto this BGG16 architecture, 19 architecture, the similar ways. From this BGG16 architecture, the concept of transfer learning comes into the picture. Okay, try reading about it, BGG16, 19, and the transfer learning script. You should be able to get it. Got it, everyone? All right. And if possible, all right, tomorrow, if possible, try to download for detection algorithms. We need to work with another IDE, that is PyCharm IDE we need to work with. Maybe try once downloading this PyCharm IDE. All right, PyCharm IDE. In case if it is possible, you can download it. So it's for 30 days. It's a trial version available. You can download this particular software. Or what you can do. So free built on open source. Maybe you can do pure Python and development. So in case if you're downloading this professional, we will be having HTML, JavaScript, and everything. We can write it here. But if it is only with respect to community version, only Python will be there, but there are a lot of things which you can do with respect to professional version. Maybe you can download this particular part in case if it is asking for any other license and everything. If it is not possible, that's okay. Just take a look at tomorrow's session, how exactly we are going to go for this yes, how exactly we are going to do this image detection, everything. Tomorrow we can take a look at it. Okay, so tomorrow we are going to get into this particular detection algorithms, how exactly this object detection is working. Wednesday, I think tomorrow is Wednesday, but all right. So this part I think we are having till Monday. So what is today? Thursday, Friday. So 3 topics. All right. I think we can learn this. You're having some more day. We learn this particular part, that is VG16, maybe VGG19, this transfer learning concept. Tomorrow I'll just teach you. Okay, so that this detection algorithm we can take it on Thursday, image processing on Friday, and text processing on Monday. All right, today we are at day 16. We are having 4 more days. It's a 20 days program. So again, transfer learning concept, we can learn it in this free session itself. No need to worry about it. All right. And we are going according to this particular agenda, whatever I've just devised. The same flow, we are just going to get into it. Any one thing that you need to do, William. William's question is, can we combine machine learning state-of-the-art algorithms and deep learning algorithm for prediction? No. Any one algorithm is used for prediction. But you can do all this text pre-processing and then you can pick up your deep learning algorithm. That you can do. But why 2 algorithms for 1 prediction? Prediction is all about only one mathematical equation. That's it. Y is equal to, if we talk about linear regression, y is equal to mx plus c. That's it. Decision trees minus probability of a log probability of a minus probability of b log probability. Only one mathematical equation. With that, we can go for the prediction. But data preparation, how we are making the algorithm learn and everything, that's what the point is. Wonderful, Anil. Great. Correct. So try to download your PyCharm, and if it is installable, try to install it. Even if it is not, that's okay, fine. Great. So that's it for today, everyone. So today we looked on to this other architectures of CNN. The architectures, whatever we discussed, nothing but AlexNet. From LeanNet we started. That's what it's a very old architecture for black and white images. And then we worked on AlexNet architecture, which is from that AlexNet architecture, it was becoming a pretty good boom. And another task is nothing but try to read about dropout function and come back tomorrow. Okay. So that's it for today, everyone. I will just share all the script files, whatever we worked on in your Drive link. You can just take the access. Okay. Take care. See you all tomorrow, 7 o'clock. Bye-bye.